Hi, everyone. I'll just try to go very quickly through the high-order mesh generation part. Let me just try to share my screen. So the tutorial that I'll be focusing mainly, first of all, can you see my screen?
Yes, it is perfectly visible.
But if you can increase the font a little bit, it's very difficult to see the content, at least for me.
How about right now, or maybe a bit?
Yeah, it's much better.
Okay, so what we have in the meshing repository is two tutorials. One which is about the mesh generation part that is completely internal. This one you will be able to do if you're doing if you're running this on the Linux on the Windows virtual machines. We just on the Mac one we just don't have one of the necessary libraries. This is a third party. But what I would like to focus is about the second tutorial, which is the industrial pipeline. So this is where we will run all the modules one by one, and we will more or less do exactly the same thing, but we will be doing the linear mesh, the linear volume mesh will be created outside of NEKTAR. So let's go to the tutorial. Victor already showed how you can run it, but as you can see here, it's very simple. What you do is just convert the mesh. And if you convert the mesh and you go to the mesh, you'll see that everything is actually compressed in a compressed format. So it is much better to be in a compressed form because obviously it will take much less time, much less space on your machine. But if you actually want to understand what is it inside, you can export it in our native XML format with this extra flag, which is XML uncompress. And if you open exactly the same file again, we will see that it's actually containing vertices, faces, and all other topological mesh parts or mesh objects. And in the end, what I would like to actually show you is, and also Victor mentioned it earlier, is that you have different composites. So these different composites will correspond to the different boundary conditions that you can apply to specific parts of your mesh. So for example, inlet, outlet, and so on. So let's open this one. Sometimes you actually can also even have the name. So if your file provides also the name of the composite, you will see it over there, and we'll use it during the tutorials. Something other that is interesting, and this is one of the modules that will take you probably, it will be probably one of the most important ones if you're running for more complex geometries. This is the mesh curving and the surface optimization, which for us, it's we call Project Cut. And as I mentioned earlier during the presentation, we just provide the step file, the linear mesh, and we would like to say, for example, an order. So what would be the polynomial order of the isoparametric curved element? And in this case, I have selected 3 just because it's slightly lighter on your machine. How does the log actually, what does the log actually tell you? So first of all, what happens is that first you load the cut file, and after that you can see that some tolerances that are always presented. So these tolerances will be different if you're running, for example, an aircraft, and different if you're running some kind of a microfluid application. So that's why we actually give you the opportunity to change them, and we'll talk about in a second. But what happens initially is that we create bounding boxes around surfaces, and that's what you see over here. Around every single surface, you have a bounding box, and you can see where this bounding box is actually spreading from. Please note that sometimes people will give a step file that is in a completely different dimension, and you can actually clearly see that here we are talking about 1.5 meters to in terms of x value, and it's probably a flat surface, so this is probably one of the domains. This automatically will tell you that you are in the dimension that you want. But very often, I have seen many people doing something of, sorry. If you go into your step file, you'll be able to see that sometimes people will give you meters or millimeters, or this will not be defined. So if this is not defined, then it's very likely that when we read it, this might be a different dimension, and obviously it will be 1,000 smaller or 1,000 bigger. So this is actually a very good indication that you have given the right format of the cut as well. Clearly, it has worked, so it has gone from 0 to 100%, and you can see that the maximum vertex correction is 1e minus 9. This is way smaller than the tolerances that we have provided, which means that we are actually we have provided a good enough linear measure, which is close enough to the cut. Another interesting information will be for you is this thing here. So if you have edges without cut and edges cut projected, this would mean that you have multi-patch elements that go between multiple cut surfaces. This is allowed. It is just going to tell you if you have that or not. And obviously, in these cases, you have a curved edges that will be projected in a slightly simpler manner. And after that, you have this module, which is the high order surface module, which is the elevation to the high order space into the cut, or projection to the cut. Okay. What I mentioned earlier is that we can actually change these tolerances, and a very easy way to do it by passing this parameter C length and doing it. It's going to be literally just multiply the parameters times 100 times in this case, and we can run it, and we can see that tolerances have increased in this case. So if you're, for example, doing a full aircraft, it is likely that your tolerance needs to be slightly bigger than if you're doing microfluids. This is the variational optimizer. It improves the mesh quality. In this case, it improves it just a bit because we already provided a good mesh, but it goes from 0.95 to 0.96 more or less. This is for the minimum Jacobian that you'll see, and you can see that even initially, we don't have any invalid elements. And finally, before we go to visualization, I just wanted to show you here about showing the Y plus resolution that I mentioned. So when we started initially, we started with this linear mesh, again, with O-type prism layer, which means you have a single very thick prism around the body. We curved it, we ensure that it's valid, and in the end, we want to as there was a discussion in the chat about turbulence models, Schwarzschild simulations, and so on, we are doing well-resolved LES usually. So it's not well model, it's a well-resolved, which means that we would like to have a very fine and very stretched elements around the body. So imagine that this is your body over here, and you would like to have this very good resolution so you can actually resolve your boundary layer profile. And the way we do it is with this process BL model, or just BL model. And in this BL module, we have to select the surfaces which needs to be actually where you have prisms. So you split the prisms that are on top of these surfaces. In our case, these are composites. And to understand where this is, we can go to the mesh file in the end of the mesh file, and we see, let's go over here, and we see that we have composites from 3 to 9. These are corresponding to faces, and these faces also are down, up, and so on. In this case, we have boundary layers or prism layers only around the wing. So in this case, this is 7, and we can execute it, and we will get the correct resolution as we would like to have it. Usually a number here would be 1.3 up to 1.8, depending on what kind of physics you would like to resolve. And finally, visualization. Victor already showed it, but in 3D, Victor already showed it in 2D, but in 3D it's slightly different. So I just wanted to show you very quickly with ParaView. And once again, field convert your linear mesh and just your the name of the ParaView file that you would like to create. This case is VTU, so just NACA linear. Same thing for the high order, and same thing for the high order with already split boundary layers. So let's just open this. Let's just open one of these cases with ParaView for visualization. And this would be the linear mesh. And you can see this linear mesh is a straight-sided mesh. If I go to surface with edges in 3D, this is actually showing your surface with edges, and this is showing you that everything is straight-sided. What we can do, however, is we can go to our next step and create the high order one. So if you use, let's say, NAKA high order, which is the one that was projected, and then we visualize that, we can do that over here. This would be slightly slower, so I probably will go to yes, I'll go directly to the surface mesh. Oh, this is loading. I just opened another ParaView session so it doesn't stop us. But in the end, I can visualize the volume mesh, but sometimes I would like to visualize the surface mesh, and I would like to see how well is the surface mesh representing the geometry. Is there any artifacts? Has something happened in a bad way? And the way we do it is with the following. In a step 8 of the tutorial, where you basically extract the surfaces that you're interested. And again, we are interested in the wing. So again, composite 7 or surface 7. And I have just selected another surface for demonstration purposes. We create the mesh. So this would create a 2D mesh in a manifold manner. And then we can do exactly the same thing with field convert and visualize the 2D manifold mesh in ParaView. Please note here that I have put N10. So this would do 10 subdivisions of the element in order to show you the geometrical accuracy in this case. So you can see over here that we have just the wing and one of the walls. And if I show you the edges, you can see that you have a lot of subdivisions on the elements themselves. But what you will see, that these subdivisions are happening on the isoparametric element, and this is purely for visualization purposes. But you can see that you have a completely smooth surface. And if it's finally ready in my volume mesh, you'll see exactly the same thing here as well. If I show the surface edges, once again, even though this is the high order version before the splitting, you think that you have multiple elements. This is purely visualization one because of using this legacy visualization VTU module that we are having. So here you still have only a single element. And in terms of the surface mesh, I think we can stop here. Finally, you have very multiple different formats that we can export the meshes. So we support mainly, I would say Gmesh is the one that we usually give to people that want to use outside of the NEKTAR family. But of course, our native formats are NEKTAR. And if you want to run big, large-scale meshes, we usually recommend people using the NEKTAR++ HDF5 format. But this is for people that would build the machine on an HPC system, and they will have significantly more options to do there. And yeah, I think that's it from the tutorial. I hope you managed to run it. If you have any problems, let us know, of course. And yeah, hope you're having a good time.